Okay, so what we're going to do is we're going to talk about what we're going to be looking at today. We're going to talk about a thing called exponential models. And with exponential models, we have three different types. We have population, we have population growth, we have radioactive decay, and we have compound interest, right? Now, population growth basically has our original starting amount multiplied by the exponential of e raised to the kt. And we're looking for whatever that k value is, and we tend to calculate it on our own. Now, this k value that we have is a growth value, so that means this k value has to be greater than 0. Now, a lot of the times we come up with these things as a decimal, and sometimes we come up with these as exact, right? In this lesson, you're going to practice the exactness for the k value that we have here, that we have right here. Now, for radioactive decay, we have this basic equation. Same equation, but the k value is less than 0. Okay, and we call that the decay rate or decay constant. Okay, so just like we said, we had a k rate for our increase in rate in money, also known as its growth rate, right? So now we also have our last one called compound interest. Compound interest is set up in such a way that you're actually compounding over a certain amount of time. And you'll notice that our R value here, our R value that is located right here, is always divided by the number of times in a year your money is compounded. You studied this last year. It's just a slightly different version of how you did it last year. Okay? Now, the biggest issue with everybody's work in this unit was the idea of the compounding different times. So if I compound annually, it's once. The special word semi-annually means it compounds twice a year: quarterly, monthly, weekly, and daily. So just make sure you have this in your stead and you're ready to go for your quiz when you get back. And so we'll wait a little bit, make sure you copy that down, and then we'll move on to our problem set. Now, we did one more. So we did all those things with exponentials. We still have one more thing to understand how to use. You're going to actually learn a thing called the Richter scale. The Richter scale is actually calculated using a thing called m. Its magnitude is equal to the log of base 10 of the amplitude of the earthquake and then we're dividing by the reference amplitude divided by the reference amplitude. All right, so let me give you an example of how this works, okay? For each model that we're using. So, example, a model of population growth in a town after t years is given by this. P of t is equal to P0 e to the kt. Let's go and write that a little better. P0 e to the kt. So remember, that's our population growth problem. So here's what it's telling us, right? Now, if we have the following, P of 3 is equal to 2P0. So this means in 3 years, our population doubles. we need to find k. So in order to find k, this is what we're going to do. You basically start by saying P of 3 is equal to P0 e to the 3k. So just remember, our original equation was P0 e to the kt, where we had P of t equaling this, where that represented our population. And all I did was just substitute in P of 3. But now we know that P of 3 in our original problem is 2 P0, which means P0 is equal to e to the 3k. Now, e to the 3k and all this stuff can actually be canceled out. So imagine if we divide both sides by P0. So now you're left with 2 is equal to e to the 3k. Now, here is what it's telling you. I need to know what exponent is equal to the ln of 2, right? So I'm actually saying, okay, when I say this, we're going to take 3k is equal to the ln of 2. So when we go and solve for k based on our understanding of what lns and logs are, we have k is equal to the ln of 2 divided by 3. Now you can leave that as a decimal, or you could leave it exact. So you got, in this case, you're going to write k is equal to 0.2310. So now that we have our k value, we can ask another problem. We can ask for another solution to our problem, right? Mathematics is awesome in the sense that no matter what you do, you always find another problem to solve. All right, so with our problem, the next thing that I could ask you is this. Find t when this is true. So now I have k as that, which means our original equation is P of t is equal to P0 times e to the 0.2310 t. So now, if I ever wanted to, I could ask you to do the following. Okay, I could ask you to find the time when our population is equal to 5 times the original population. So we can go back to that problem that we did before and use our basic equation here. So now let's do this. So we say, all right. So we say, okay, 5P0 is equal to our original equation. P0 e to the 0.2310 t. And then we divide both sides by P0 to get rid of that initial population. So we're saying, what exponent do we have to raise e to get 0.230t, 2310t? So all we end up doing is we just take the ln of both sides. So if you think about it, just take the ln of both sides, and this means the ln of 5 is equal to the following: 0.2310t, based on what we know about logs, right? So now when you solve, you divide both sides by 310, and then you get your decimal. And in this case, t is going to equal 9673 years. 6.97673 years to grow to 5 times. Okay, and that's it. We're done. Okay, I'm going to give you another problem here. So this one is dealing with a thing called decay. All right. So imagine that we start with 20 grams of radium. So after T years, the equation that represents the remaining, that shows the remaining amount, is A of T is equal to A naught e to the negative 0.000418 T. Okay? All right, so here's what I'm going to ask you. Find the remaining amount okay, after 100 years. So here's your solution. Ready? So you start with A of 100, and you just plug it into the equation. So remember, A0 was 20. So we put 20 e to the negative 0.000418 times 100. Okay, punch that in your calculator, and you end up with 19.182. So you can say, therefore, after 100 years, there are about, let's say, 19.812 grams remaining. And we're done. Now, your 2 other examples I've posted online, so you can copy those down. And the 2 examples that I've given you are a model using compound interest and a model using an earthquake. You'll have one of each problem to do on your final task. So I just want you to do these 5 questions. They cover a gamut of the basic problems that I asked you to learn. That's all I need you to learn for this unit. And when you get back, I expect you to be able to do at least lessons number 1 through 5. Lesson number 6 is a bonus question on your test, on your quiz. Okay?